Okay, it's my pleasure to welcome Guofang Wei from the University of California in Santa Barbara, who will speak on singular Weyl's law with Ricci curvature bounded below.
Okay, thank you, Caroline, for the invitation. I thank the organizer for organizing this wonderful seminar, which I have been attending and learned a lot. Okay, so today's work is based on this paper we just already posted on arXiv, and it's joined with Xianze Dai, my colleague, Shuhei Honda, he is in Japan, and Jiayin Peng, he is at UC Santa Cruz currently, but he was a former VAP at here, UC Santa Barbara, and that's how we start. Okay, so basically, maybe the plan is a little bit, let's introduce what is Weyl law. That's something actually I picked up recently only. And then we will state the result. Okay. So Weyl law is about think asymptotic behavior of the eigenvalues. So which I think actually some of you studied a lot in spectral geometry. So here, eigenvalues are referred to the eigenvalue of Laplacian, and it depends on whether domain. So I'm going to concentrate on the domain which are compact, so it's easier. In that case, the eigenvalues are all discrete. So basically, lambda is eigenvalue if it satisfies this equation, and we put a negative sign so that, and this Laplacian here in the Euclidean case is just a summation of all the derivatives. Okay, so in order to make a lambda non-negative, we put a negative here, just the two. Means we like positive number better. So we could be no boundary, then this there's no boundary condition, or one can put Dirichlet boundary condition, which means vanish at the boundary. In that case, first eigenvalue is always positive and always go to infinite. Newman case, first eigenvalue is always 0, or if closed manifold, because we can take the function to be constant function, will automatically satisfy the equation trivially for lambda equal to 0, a constant function. And so this 0 is always first eigenvalue. That does not work for Dirichlet case. If you take a constant function, then the boundary won't be 0, then the function has to be 0. Okay, so in order to be eigenvalue, as we said before, the function cannot be identically 0. So it has to be a non-trivial function. If we have a non-trivial function, satisfy that, right? So there's lots of study about eigenvalues, which are interesting in mathematics and physics, because in physics, eigenvalue is kind of the energy level measures in quantum mechanics. So Weyl law is just a look at that how we know that eigenvalue always going to go getting bigger and go to infinite. So how fast is going to infinite? And that is a Weyl law described. So first studied by Weyl in 1911. He did it for domains in Euclidean space, the plane and the R3. So I will state the version actually for manifold, which is really the same. Okay, any comments, questions? Please feel free to interrupt. Okay, so actually we can just let's state the version for closed manifold, closed Riemannian manifold. So precisely how do we measure how fast it goes? One way is look at so-called counting function. Basically, given any real number lambda, you count how many eigenvalues there are smaller than lambda. So this is a counting function, which measures how fast the eigenvalue grows actually equivalently. And there is a really nice general formula say this this function, okay, of course, when lambda grows, eigenvalue get more and more, so it's going to grow. It's look exactly like lambda to the n over 2. Then this limit always exists, and it's equal to some canonical constant times the volume of the space. Right? Okay. So this doesn't matter what the manifold is. Asymptotically, somehow it's only the volume of the manifold is coming in this case. Okay. So the constant is all same for any manifold with fixed dimension. This really captures how the eigenvalue grow, because if, let's say, I look at lambda k, I take lambda to be the case eigenvalue, right? So that means m lambda, there's k of them over lambda k of m over 2. It's like a constant Cn and the volume. So therefore I put in over, so that means lambda k is like a k to the 2 over n plus some constant and the volume. Well, the power here also. The power is outside. Okay, let's just put some constant. Anyway, so the key is the eigenvalue. We said it's always growing when k goes to infinite. How fast is grow? It gives you exactly the power. So that's amazing about Y law. And this same Y law exactly works if you look at a domain with boundary, Dirichlet boundary or Newman boundary, and it's exactly the same. Okay, so it cannot really tell in here what is the boundary condition we're using. And if you look at the so-called manifold with weighted measure, so you have Riemannian manifold, you change the measure to another measure by e to the negative f, like a conformal change. Then you also change a Laplacian to be the, okay, so Laplacian in the definition, it depends on the measure. You see, you define the Laplacian, this so-called weighted Laplacian or weighted Laplacian, so that with respect to this measure, this Laplacian is still self-adjoint. Okay. So Laplacian is modified, measure is modified, and we can talk about the eigenvalue of this and satisfies exactly same asymptotic. Okay. Here. Any questions? This okay, so hopefully this gives us some idea what is Y law mean, but this has been, I said, studied, more than a century. There's lots of works, and actually for me it's first time I study this. But maybe if this hasn't really make you interested, maybe let me make a side like a remark about the Y law. There's still very basic questions open actually. So this is not exactly related to the work I'm going to present, but I thought it's very interesting when I learned earlier. There's so-called Pauli's eigenvalue conjecture. So if you look at Pauli conjecture, there's a conjecture about number theory, and it will come. But he made in 50s about behavior of the eigenvalues. This is about domain in Euclidean space. Okay, specific. So that's, and this what he conjectured. So for domain, we said we can consider the Dirichlet case and Newman case. Then, okay, asymptotically, they both in the end, the counting function is this constant volume times lambda to the n over 2, right? So that's exactly what we expect. But the conjecture that it's Dirichlet case, then for all lambda, this is for all lambda greater than 0. The number function is always smaller than the asymptotic come in, while the Newman is always big or equal to. Okay, So this is not just the asymptotic, but it's strictly strict inequalities in this. So asymptotically, we know this is the number. But for all lambda, this is the limit goes there, and the Newman is opposite. So this hopefully intuitively why this is less, and you know the Newman the Dirichlet eigenvalue, if you count them here before, we count them by multiplicity. If you count them by multiplicity, okay, so the Dirichlet eigenvalue is always smaller than Newman ones. So then the number function is always smaller. Okay. Sorry, I should say opposite. The Dirichlet eigenvalue is bigger than the Newman. Remember, Newman starts with 0. Therefore, the number function is opposite. The number function of Dirichlet is smaller than the Newman, right? Okay. Because at the same lambda, these eigenvalues are smaller, so you pick more. There's more of them in this. So this is always true. It does not have to be Rn. Any domain in manifold, it's always the case. Okay, so this in the Poirier, he made the conjecture in the 50s, and he verified that it's true if the domain tiles like the plane or the Rm, namely if it's a let's say rectangular shape, like parallelogram kind of thing. If you tiles the plane, then he proved it's verified. Actually, he only did the Dirichlet case, but kind of similar proof works for Newman. Okay, so that's actually, well, there's some little bit other things, maybe multiply this tile stuff. But for a while, actually, this only very recently, actually, by these 3 people, they showed that it's also true for unit disk in the plane. Actually, part of proof is analytic, part of proof they use a computer to verify it. For lambda small and lambda big, they verified. So they showed this is true. So this is still, you know, I thought this is a very, very basic, so look like a naive conjecture, still very open. I think this is the first time this domain does not tile and it's verified. And came across very recently, also somebody studied, you can ask the same question for domain on the sphere, and then this is not true. These 2 functions cross each other very often. These 2, the asymptotic and the function cross each other very often. Yeah. Okay. So this is a side remark about Weyl laws. Maybe I'm not sure. Hopefully, you think that this is it's still quite interesting, you know, even for domains in Euclidean space, there's still conjectures open. Yeah. Questions, comments? Okay, now let me come back to our result, what we want to study. From the title, we said we want a so-called study Weyl law for singular space. Okay, these are all very nice. So what is the singular space I'm referring to is the so-called Ricci limit or RCD space, which been studied a lot. Okay, actually they're really kind of nice space too. So what is the Ricci limit? It's just the Gromov-Haus limit of manifold with Ricci curvature bounded from below. That's usually referred to Ricci limit space. Okay, if you add the assumption that the sequence of volume is also bounded from has a uniform lower bound, then it's referred to non-collapsing Ricci limit space. Okay. So this occurs naturally as a limit, right? In order to study the manifold with Ricci bounds, it's natural to study their limit, and studying the limit also give back information about the sequence. So they are really correlated, and that's why we study them a lot. So then the recent, it's also been very active, so-called RCD space. So I will not define the precise definition. Instead, RCD space is a metric measure space. So it has a topological space with a distance and a measure. Okay. So all Riemannian manifold also comes with it, right? We said, okay, it's a Riemannian manifold. It has Riemannian metric, right? That implicitly induce a distance and a volume and a measure, which is, so the Riemannian metric induced distance. So it, maybe we don't write them that way, but Riemannian manifold also is a metric space with measure. So we say RCD means the K means the curvature is bounded from below. It's kind of like a Ricci curvature, and M is for dimension is bounded above. So we don't have precise, it's just the dimension upper bound. And R, so that's for CDKN. R is referred to Riemannian. And that here, just we can interpret that. In this case, you can still talk about the Laplacian and so on, and even talk about heat flow. So here the heat flow is linear. That is referred to the word R here. Okay. So instead of saying, make the definition precisely, I'll just say this is like a synthetic notion of Ricci curvature low bound to metric measure space. And the space we are most interested in, right, it's the Ricci limit space. The Ricci limit space is RCD space. So if I have Ricci lower bound and manifold, then that passes to the limit. So that's one of the really good thing about RCD space. It's kind of stable under Gromov-Hausdorff limit. If the sequence is RCDKM, then limit is also RCDKM. So it's really nice. Yeah, so we can essentially focus on this or think about using the Ricci limit space as an example, because in fact, all the known examples of RCD space are also Ricci limit space. So we don't have a non-trivial example in that sense. But making it RCD, it's intrinsic, it also make it study more convenient. Lots of things. So these are the spaces I'm going to focus on. And in people in another category, it's, well, I guess I should maybe say it's another category, it's Alexander space for people studying with sectional curvature, and those are also RCD space. Okay. So since they are singular, so then we want, as we expected, so I not go in, this space topologically could be very bad. Locally could have infinite topology. Namely, you could have space that at a point, no matter how small the neighborhood you choose, the second Betti number is infinite actually. Okay. But recently, I hope that one can prove that these spaces are semi-locally simply connected, so still has some nice topological structure. Anyway, for singular space, so we want to, define which are the good point and not so good point. So good point, we call them regular point. So those kind of space, at every point, you can blow up. Looking at closer and closer, like you're magnified. If all the tangent cone is nice, like Euclidean space, just like a manifold, all the tangent space is unique. It's really, C infinity close to Rm. And those we call them good point. So if it's K, then it's K regular. If it's not for any K, then we refer to not so good, which is a singular point. Okay. So that's usually the notion, for any not so good space, singular space, you can distinguish the good point, bad point by looking at infinitesimally how they look like. Okay, looking at it very closely, right? Okay, one very maybe fundamental. This is all actually all the result. Usually it's first done for Ricci limit space, then extended to RCD space. So you put all the regular point together and singular point together. Well, okay, so let's say RK is a K regular point, actually specific. Then there is a very nice description about this regular singular point by Breuer and Daniel Samala. So this earlier it was coding neighbor showed for Ricci limit space. It showed that actually there is one unique K, and the K has to be a natural number. It's integer. It's between 1 and n. So this is RCDKN. Okay, so K cannot be bigger than n. Such that so for this K, the regular set has 4 measures. Okay, because this RCD space, it always has a measure. So with respect to the measure M, it has the 4 measure. So which means the singular set has 0 measure. And you can check that the Hausdorff dimension of the regular set is also equal to K, so somewhat compatible. Okay. So for RCD-KM space, before, we only know the dimension is less or equal to n. Usually you don't know exactly what's the dimension we can define. But from this result, we can associate to an RCD space a dimension with namely this unique K. Okay, so this K is an integer, and its K is between 1 and n. And this K sometimes, usually it's referred to rectified dimension of the space, because this regular set, they are rectifiable. Okay, so this, and it is a unique K associated to it. So we can talk about dimension of the singular space now from this result. Any questions? Okay, so this is my object. Okay, so all you need is you can just think about just RCD space. There's a regular set which has 4 measure, singular set has 0 measure. Okay, and the regular set is K regular for some unique K. Okay. So now I want to study the Weyl law of this kind of space for so-called this either Ricci limit and RCD. There's not too much trouble. So they already early work on this. One of the things is in the case, the K actually is maximal. So we said this dimension is from 1 to n. If K is maximal, actually it showed that equivalently, that means the measure has to be Hausdorff measure, actually, up to a constant. Okay, so then in this case, a very similar Weyl law, it's almost exactly the same as a manifold case, except right, we change the volume of the manifold by the Hausdorff measure of the space. So here I'm still, it's compact space, okay? So we can talk about, eigenvalues are all discrete, so on. And since this is Hausdorff measure up to a constant, it's the same as the measure of the space. So you can just, this is also measure of the regular set. Okay. So this is the first done by Dean based on early work of Chiga coding on eigenvalues. So this is first, he showed for non-collapsing Ricci limit space first in 2002. Then recently, Luis Ambrosio, Shuhei Honda, my collaborate, and David, they did it for RCD space. Okay, so this, and in some sense, their RCD space, they in some sense look at the Newman, namely they don't have the boundary conditions. And also independently, Zhang and Zhu, they did the Dirichlet case. So they studied for compact RCD space. Okay, so in here, you also assumed so-called non-collapsed RCD. So when we say non-collapsed RCD, it just means measure is a Hausdorff measure. So in general, when we define RCD space, right, this distance and the measure could be just independent. They're not correlated. But if you have space with distance, it always induced a Hausdorff measure. And if that is h to the m is the maximum possible, then it's called a non-collapsed. Okay, so in this non-collapsed RCD space, I'm saying the exactly same Weyl law. So it captures a regular. So we sometimes call this is still a regular Weyl law. And in particularly, that means it's exactly same works for Alexander space, because Alexander space are really RCD space, a non-collapsed RCD space, right? When we talk Alexander space, we implicitly, the measure is a Hausdorff measure. Okay. So that all work really nicely. It's the same asymptotic. Now, if it's collapsed, namely K is strictly less than M, Ambrosio, Handel, and they also have a result. Their result is still captured by the regular set. So K is a regular set. They make it a little bit smaller. They call it reduced regular set. So saying asymptotic, but there's a need an assumption. The assumption is that this limit of the measure of Rk going to 0, when R go to 0, the limit and integral commute. So you can take the limit to the inside and it's finite. If that's the case, then asymptotically it's like this. This is the K's Hausdorff measure of the regular set. So all of these we visualize as a regular Weyl law. So this is regular. Even though the space is singular, right? The asymptotic what come out, the measure is on the regular set here and here. Okay, so any questions?
Small notational question. What's the star on the RK?
Oh, excellent. Yeah. Okay. This is office to be precise. It's called reduced regular set. So it's a subset of regular set, but still has full measure. Regular set. Okay. So it's those regular set such that the measure at that point, regular set, it's like a so-called all of regular. That is the assumption.
Okay, thanks.
Namely, the measure is both sides bounded by like R to the K. The measure of the ball of the point X to the R up to some constant. So that's a subset of the regular set, but one can show those are still have full measure. So therefore, this Hausdorff, yeah. So MK, if you look at the usual measure, this star of K is still equal to MX. Thanks. Yes. Okay. Right. Okay. So far, actually, people don't have example of this is a reduced regular set and the regular set are different, but in the proof they need that. Yeah. They could be the same, right? But right now it's a subset, but still has full measure. Okay, so that is a regular Weyl law for this. Now I want to present our result, which tells a quite different story. So this is a recent joint work with Day, Honda, and Pam. we can, okay, so in this k, remember the k is either like the m, it's always integer in here. So now we can show that the Y law, the power could be any beta here, could be any number. So beta may not be integer at all. So it could be, you know, fraction or irrational number in this. So for any beta, we can find a compact, yeah, with RCD space, the curvature we normalize to -1 and some dimension m. If beta is big, then our n also need to be big. So in this space, the rectified dimension is still 2. It's very simple. It's actually, we'll see the space itself. It looks very simple, actually. So rectified, so the k is equal to 2. But in the Weyl law, this as a power is captured by beta. So we said beta could be any number. And not only that, what it occurs, this is Hausdorff measure of the beta of the singular set. Okay, so it's not the regular set, it's a singular set. So that's what come out of the asymptotic. So I don't know, that's why we call it singular Y law. It's not just that the space is singular, but this before it was volume of the space, right here it's Hausdorff measure of the singular set. Okay. So this is one type. Another type actually come out saying is we can also exactly in this space. So okay, so here the Hausdorff dimension of this space is actually beta in the above. Now I have a space with Hausdorff and a rectified dimension both equal to 2. Okay, so this space we can make m to be 10, of course. If it's bigger, it's even more. So curvature again is -1 RCD. In this case, the asymptotic is not any power. It has a log term. So it is lambda of log of lambda. And then again, this captured by Hausdorff dimension of the singular set, of Hausdorff 2 dimension of the singular set. Okay, and it's precisely 1/4 pi. 1/4 pi is if you look at manifold dimension 2, then well, the power should be the regular good power, then this is the same number. It's also 1/4 pi in this case. Okay, so this is quite surprising, as means RCD space are still in some sense quite nice spaces. And this is almost like a behavior of fractal, you know, those they have fractional dimension and has a log term. In the dominant term, in the expansion already have the log. Usually it's only in the later, you know, actually I said the Weyl law, we just look at the first, the expansion from the first term. You can look at the later order terms too. So in this example, well, you said what is the Hausdorff dimension of the whole space? Actually is infinite. So this is really only the singular set. Okay. So it's quite unusual and surprising in some sense. Any comments? Maybe? So,
please, there is some relation between this beta and the beta flatness condition.
the relation between the beta and what is to what?
With the beta flatness condition for lambda.
Oh yeah,
There
this
is
is lambda, the lambda to the beta power, beta/2. So in some sense, in the manifold case, what's lambda to the n/2, right? And n was the dimension. And in this case, yeah, in some sense, beta is the Hausdorff dimension of X. And that's where this come in. In this example, beta is the Hausdorff dimension of X. Does that answer your
It's
question?
okay, thank you.
It's okay. So here, yeah, all right. Maybe I should say my beta is big or bigger than 2 here. So this space, you know, the rectified dimension is 2. So, but Hausdorff dimension is bigger. So it's capturing the Hausdorff dimension of the space, not the original measure. Okay, not original measure. You know, for original measure, the singular set, it always has measure 0, right? So it's really capturing the Hausdorff measure in the Weyl law in some sense. And that's maybe sometimes makes sense because if we look at the, you know, Weyl law, it's look at the infinite lambda getting bigger and bigger, then it's like infinitesimal. So which relate to more like a distance in some sense. Okay, so another part, I don't know, it's about actually from the feedback is the singular set. So we said the measure of the singular set is equal to 0. So this is, in terms of measure, this is small. Actually, this singular set is even more small in terms of the so-called capacity. So if we make this m relatively big, we can make this a singular set. So we said, okay, fractal, this could be happen. And this, we were told that even fractal, they don't have this behavior. So in our case, we can show this singular set has so-called null capacity. Okay, so this is something new. What is a set in a big set? What's the capacity? It's like the, you know, physics, how much electron you can hold. Okay, so you look at this energy function, energy, and you look at all the, take infimum among all the f, which on the set A is 1 in a neighborhood and outside it becomes 0. And as you look at the smallest energy, and that's the capacity of the subset. So capacity 0 basically means this H1P, it's the same as you take out the set A and look at the Dirichlet boundary condition. These two Sobolev spaces are the same, okay? So what we can show in our case is this singular set actually have capacity 0 for any P if M is big. So this is not just a measure 0, but the capacity is really, really small, okay? On the other hand, if we look at the eigenvalues, because these two Sobolev spaces are the same for H12, that means eigenvalue of X is the same as the Dirichlet eigenvalue of taking out the singular set of Dirichlet. So from the eigenvalue, you look like, oh, it's all look at the regular point Dirichlet. But on the other hand, the Weyl law really, it's all captured on the singular set. So this, I think we were told that even in fractal, they don't have an example like this. Namely, the Weyl law is concentrated on this singular set as a very, very small measure 0 set that capacity actually equal to 0. Okay, so that's okay, only if you're interested in, maybe in statistics, people more interested in this. All right, so now the rest of time, I don't know any questions, I will maybe start talking about the proofs. Okay, so the proof divided into many steps. Actually, I feel like I prepared a little bit of challenge, maybe too much, maybe. Okay, so let's see how it goes. Okay, so the starting point of the proof is work based on earlier example I did with PAM, which just appeared in GAFA. We show that for RCD space, or actually, sorry, Ricci limited space, we can find a space with positive Ricci curvature, such that so-called asymptotic cone. Basically, it's cone at infinite. It's 2-dimensional. It's a singular set, you know, with a regular set of 2-dimensional. So that means the rectified dimension is 2. Okay, but the Hausdorff dimension is 1 plus beta actually. So that's why. actually, let me see, this beta and the earlier beta is, I think we used it a little bit differently. Well, okay, yeah, so this beta is the 1 plus beta over here anyway, so let's not. The 2 beta are a little bit different. Okay, but so this 1 plus beta was previous beta in sense. Anyway, so this basically saying that now if I choose a beta here bigger than 1, then my space, the Hausdorff dimension, is going to be same as Hausdorff dimension of singular set, which is bigger than the regular set, because Hausdorff dimension of the regular set is equal to 2. From before we said at the regular set, it's always the Hausdorff dimension is exactly equal to the RK, the K factor in this case. So this is the first time really showing that, you know, we set the limit measure of the singular set is 0, right? Equal to 0. But the Hausdorff measure is the Hausdorff measure of the regular set in here, of course, of the beta is equal to 0. So that it really shows the limit measure and the dimension, the Hausdorff measure, really, they are very, very different. You see, for the usual measure, the singular set equal to 0, but for the Hausdorff measure, beta bigger than, it's a regular set equal to 0. So in some sense, they are kind of opposite. So this answers the question. More than 20 years ago, Chiga-Codin, they asked this question about Ricci limit space, whether the Hausdorff dimension of the singular set cannot be bigger than Hausdorff measure of regular set, because in terms of the usual measure, that should be the case, right? The usual measure, the regular set has 4 measures, so singular set is kind of smaller. So ask, is that the same for Hausdorff measure? You know, Hausdorff the singular set could be smaller. If that's the case, then the regular type dimension and Hausdorff dimension are the same. So this is, of course, in the non-collapsing cases true, but in the collapsing case, we show this is really no. That's the answer, because we have the Hausdorff dimension of the singular set. It's much bigger than regular set, as actually as big as we want if we pick this m bigger. Any questions? Okay, okay, so how this example is constructed, let me maybe say quickly. These examples actually go back in the 80s by example of Nablan and Boulard-Bourgeois and myself. We were trying to construct open manifold with positive Ricci curvature, but so Nablan first showing that the fundamental group could be infinite. And later I showed that the fundamental group, in fact, could be nilpotent. Okay, so similar construction here. So now here, let me just do the simplest case. It's the manifold is just Rn warp product with S1. So this is a double warp metric. So you can think about the interval, the ray, and this is together, it's Rn. It's a warped metric. And this is S1, right? So therefore, the fundamental group of this space is Z. And we use a warping function, which I constructed in the nilpotent. So the key is that this warping function f is growing, but not growing too fast. So like square root of r. And h actually is decreasing to certain power. So h is small in that sense. And in this case, if you choose m bigger, notice like this Rm, this has positive curvature. And S1 itself has 0 right curvature. And if m big, then we can use a positive curvature to help with 0 so that together it has positive Ricci curvature, basically. So n need to be big then the alpha in this example. Okay. Oh, so this picture is draw my collaborator, Jiayin Pan. He is in the audience. So maybe you can show this part. It's you can think about this. It's a half cylinder times S1. So S1 is getting smaller and smaller. Okay. Then this half cylinder, you rotate it by the sphere. So this sphere are getting bigger. This is S to the n minus 1. So all around on all the sides, you have the sphere, and this sphere are getting bigger, but not too big. It's like square root of r. Okay. Since they're not getting too big, so therefore, when you look at the asymptotic cone of this manifold, actually, then everything shrink. It will just okay. It will shrink so that the asymptotic cone is array. Okay, but now what we study, and this is the thing, what we study is new, is that we look at the universal cover of this. So this is M. We look at the universal cover of this one and tutor, right? Because it has fundamental group. It has fundamental group Z, so it's going to unravel and use the symmetry a lot. Then you look at the cone at infinite. In this time, it will have this not just array, it will pick up the R factor from the fundamental group. Okay, so that's our Y. So topology, this is very simple. It's 0 to infinite times R. Okay. So this has these features I talked about, and the singular set basically is, so Y is now it's just this part. Singular set is on this array, and everything the regular set is this part. And this example actually, haven't maybe was studied enough. Inside the remark, Peng and I actually using this example to also give a negative answer to an open question, maybe more than 50 years, about the Boltzmann function. Namely, has been open, I think, when Chiga-Gromov, they proved the splitting theorem. For sectional curvature non-negative, Boltzmann function is always proper. Okay, so Boltzmann function, it's like a distance function from infinite, normalize it. So I think. So is it true for non-negative Ricci curvature? And there's lots of partial results showing yes, it's the case by Christina Salmani and Dongmin Xin, like if the volume growth is maximal or minimal. But using these examples, okay, we showed that in general, it's not true. You have positive manifold with positive Ricci curvature, and the Boltzmann function is non-proper. Okay, so we also use this example. Okay, okay, but that's not. We showing that this example actually is telling a lot, but it's not directly about our Weyl law in this case. Okay, so now let's come back to prove about the Weyl law. Okay, so we want to look at the asymptotic of this counting function and lambda, right? Maybe lambda is. So there is a very classical called a Kalamata theorem. Originally due to actually this if and only if, I think one direction is called abelian, the other direction we're going to use is Tauberian. So abelian is Abel actually. It's saying this asymptotic. So let's take this L to be taken out to be 1 first. That's just then this asymptotic of this function, counting function, to lambda to the some power equal to constant is exactly mean. Remember this, we look at all the eigenvalues, take the exponential and take the sum. It looks like this, gamma to this power here. T is square root of the alpha. So this is yeah, okay. Kalamata gave a simple proof of this in 1930s. And also you can add so-called slowly varying function. What is slowly varying? Means limit of this for any a positive, it's always 1. So what's the example of slowly varying function? Like L is constant function, of course, it's satisfied. And that's like the 1 we said. And another typical example is the log function, or power of the log function, or log function, or log plus t. But if you have constant like 2 plus sine t, then it's not slowly varying function. So if you add a slowly varying function, this is also true. Okay, so because 1 over asymptotic we have was a log. So we, okay, so the key is this for compact space, this summation is really just as a heat trace, we said. You take the diagonal and integral of the space, and that's it. So now from this theorem, in order to study the behavior of this counting function when lambda go to infinite, it will reduce to study this heat kernel when this t go into 0, small time. Okay, it's translated this one when t is small. Okay, and this is the first tool I think standard has been the case to use in this case. Now about heat kernel, there's a so-called Lyell's estimate on the upper and lower bound. Of course, before it was done for manifold with Ricci curvature bound. Now it's extended to RCD space or a while back. Okay, based on several works. Basically, heat kernel, and if you multiply the measure, it's bounded from both sides. Okay, in terms of the distance and the curvature bound. If the curvature is 0, the k equal to 0, then the second constant is 0. So we can take that out, the C2, if k equal to 0. So while we only need to look at the when x equal to y, so basically this term is also, distance is also gone. So therefore, if we look at the term of the heat kernel, because we tired of putting square root, so we make it S to be square root. So if you look at the heat trace times the volume together, then this function is bounded, right? Okay, so now key is to study the heat kernel. We go into studies now depends on this is one of the volume and another is the Q. The thing about a Q, now Q is bounded now, all right, from both sides. Especially the one we have the curvature equal to 0. Okay, so now it looks like volume kind of more easily to deal with it. So that's why we're going to study these two separately. Okay, so to study this, heat kernel, it's almost impossible to write them explicitly, even for manifold. Maybe iron you can do it, and a comb, metric comb, probably that's it. So now we need to study this for our space. So the first thing we do now with real work start. First thing we do is we look at the examples we construct earlier, Y, and we look at those properties. And we found that actually the Y is, remember, it's just really just array times R. This Y, the metric, can be written very explicitly in terms of Riemannian metric, but singular. When I equal to 0, this blows up. Okay, so it's incomplete Riemannian metric. It's very explicit. And the measure we can compute also very explicitly in terms of this coordinate R and V. So from here, you can immediately see, okay, when I equal to 0, it is a singular set. This measure, when M big, this measure is very, very small when M is big, right? Because you have this power of R to the M. So that's why the singular set, the measure is very, very small, can be as small as you want. Now, a very important property we discover is so-called the dilation property. Namely, you take any point and you dilate in terms of this power, R is just a lambda R, but it's a V direction. So in here, this is it's a half ray. So let's take this out. So this is R and this is a V. Okay, so by some power, then this is a distance. This is keeps it. It's just the distance between the point. It's just by scale, and the measure also by scale. Okay, so this kind of property is a very special. I think in manifold only Rn has this kind of property, and Alexander space like a metric cone has the property. Okay, Carnot group has a property, but that's not an RCD space, not even a CDKN space. So this property is a very, very special. We use it strongly to conclude. And if you want to see why this Hausdorff dimension here, we use the alpha, it's 1 plus 2 alpha. You notice the distance from the this point here to this one. It's instead of the V, the usual, it's V to the power. Therefore, we can see the Hausdorff dimension is here is in this language is 1 plus 2 alpha of the singular set. Okay. All right. So now this metric is very, very explicit, but to construct the heat kernel is still not a big challenge. Even actually to compute the volume of the ball, that's what we need, right? We need a quantity of these two controllers. But we really use a scaling property to, so the volume of the ball to control it is still very direct. It's still not easy at all. So we use this dilation property to send it to infinite. We can compute the asymptotics, and instead also we compare to the volume of this rectangular domain. Rectangular domain one can compute explicitly because the metric is like a rectangular, and we can compute the asymptotics. So that's, we take care of the volume 1 over. That's what we needed. I think let's not skip that. Then next thing we have to focus is the heat kernel. Okay, so the heat kernel, now we really also strongly use the symmetry because this space, the space Y, right, is in this direction. It's there is a action in here as isometry. So everything, it really only depends on R. In this space, actually, it's symmetric, right? It only depends on R because the V direction is symmetric, everything. So like everything ODE. So then, so we can just depends on the R. Everything does not depend on the V. So in this case, then it scales. The heat kernel, it also scales. So now, once you have this property, we can write this heat kernel in terms of what we had before, in terms of the ball, and it's a heat kernel scale, so I can only look at the 1. So we want to look at this behavior, right, when S go to 0. Remember, that's the difficulty is that we cannot take limit inside. That's a good look. It does not commute. So we have to first commute and take the limit. Okay. So from that, we can compute that this integral, there's a singularity probably at, okay, we have to rescale, and this at infinite and 0. At infinite, this is always convergent, but at 0, it looks like this. So it could be a divergent. So when alpha is big, it's convergent, and this limit actually is finite. But when alpha equal to half, it's divergent, and we can, with lots of analysts, we can show that it divergent look like a log. So it's slowly varying. And from here, can show it looks like a log function. And that's the other example coming up. Okay, so this part is quite technical. Now, all of this work is on the space Y, which is non-compact, right? To reduce it, we need to construct a compact one. So we first take Y and take the quotient. Y is, so then we got this. It's like this is a Y bar. Then I cut off slow, make this to be flat. And here I make it so that it's flat outside. Then I glue these two of the copy together. And that's my X. This is compact now. Okay, so one thing is that even though the Y is non-negative Ricci curvature, but X has to be, this K has to be some negative because we did the gluing. Actually, it's impossible to make it a non-negative because X has this closed geodesic, which will become a line is a universal cover, but X does not split. Okay, so that's our compact space. Then we need to keep track how the heat kernel changes from the Y to X. Okay, so we have two procedures. One is carving and one is gluing. So we keep track how carving, there's a relation between the carving space, the heat kernel, and the top. And use a distance estimate. We can show that when going to 0, they behave the same. And the gluing, we can also keep track, namely when S is small, it's actually just basically Y, not because of the gluing, there's copy of 2 in this case. Okay, so sorry, I apologize, this going fast. Anyway, so there's several steps, procedures to keep track how the heat kernel end. But then once you have reduced to the Y, we have very good understanding of this, and that's it. Okay, all right, so yeah, thanks. Okay.
Thank you very much for a really interesting talk. And
Thank you.
Are there any questions?
Sorry, I have a question. I'm Shamari. Thanks for your talk. It was really inspiring. I was wondering whether you have some guess of how, if it has to change, how could it change the Weyl law for minimal submanifolds? There is a Weyl law for minimal submanifolds. If you have some singularity, do you have some guess on how could it change? You expect they could accumulate more faster? It's a law for the width, for the growth of the width.
So you said there's a Weyl law for minimal submanifold specific, which has a singularity.
Exactly.
Okay, so are those spaces still has some kind of a Ricci curvature law bound, namely so-called RCD space?
Well, let's assume you are in an RCD space.
Okay, so
kind of
yeah, actually, so I don't know. My conjecture is that for RCD space, the Weyl law, what it kept out, the power at least, is always associated to the Hausdorff dimension of the power of the space. Yeah,
okay.
That seems to be more relevant, the Hausdorff dimension instead of the original measure.
Okay.
So yeah, our intuition is here from C, we want to study the heat kernel when T is small, right? When T is small, the heat kernel captures the distance more instead of the whole melt. Instead of for a long time, we are looking for short time.
Okay.
But yeah, I don't have idea to prove that in general yet. But this example is showing, yeah, there's lots of different stories when can, different from what had expected before.
Okay, thank you.
There's a question in the chat asking about other applications that you might be looking at or whatever.
Right. So one could, yes, should still study the general RCD space, but main thing I think this is really, this example is telling a very different story. Also, I think it's this example itself is very interesting. We want to study. This is utility only two-dimensional in some sense, right? Hausdorff, you could, well, Hausdorff maybe higher. So there's especially the other one, it's Hausdorff dimension 2 and rectified dimension 2. And this, I feel like this example is saying a lot more you can actually study about this kind of space, because if anything dimension is smaller than that, it can, and this is maybe the simplest example, which is not Alexander space, but two-dimensional. Because if the dimension is lower, RCD, and it is, then people already proved it has to be same as Alexander space. So this example, as I saw before, like, you know, we have application to Boltzmann functions. So I feel like this example has potentially, there's more story we can investigate. Okay.
Are there other questions? Or? I have a small question because I haven't really worked with RCD spaces at all. But yeah, I found the results really surprising and interesting. But just a small question. So the N in the RCD-KN, the synthetic dimension, how does that relate to the Hausdorff dimension or the rectifiable dimension? Is there, what is the difference?
Right. Yeah. Okay. So the rectified dimension, if KN, the rectified dimension, if we start, this is a bigger K, it's a small K, it's always smaller than N. And that's the rectified dimension. If it's equal to M, that's usually they call it non-collapsing. That's like the manifold case. This dimension, it's always equal. Okay. But on the RCD, it could happen that this rectifier is smaller than N. And Hausdorff dimension, it's also always less than M. So this M is always a bound of everything. So Hausdorff dimension of this maybe beta. This is Hausdorff dimension of this. This beta is also always smaller than N. And before the people expect this the beta is smaller than K, but that, so beta and the K is a relation, one could be bigger than. So the K and the beta, now they show they don't have one could be bigger sometimes or smaller. They don't have to be, both could happen, but both of them is smaller than N. This N, the bigger N, the synthetic dimension, yeah, the upper bound dimension.
Okay.
So this really solve upper bound of the dimension. It's upper bound of Hausdorff dimension, it's upper bound of rectified dimension. But if it's equal to M, that's like it's the usual, we study the manifold case, it's equal. Yeah.
Okay. Thank you.
But yeah, if it's a Ricci limit space which is coming from collapsed, so this M is the same as if we have sequence of manifold and collapsed, basically like a torus collapsed to a low dimensional space, X. So this X, then this X, we still satisfy the Ricci bond with the same M, but the space X itself could be lower dimensional. That's why.
Okay. Oh, I see. Okay. Okay, thanks. Are there any other questions? If not, thank you again. It was really interesting.
Thank you. Thank everybody.